Hey, welcome back. This is 8.4 trig subs. These are probably one of the more complicated types of integration techniques, and it's kind of like a last resort type scenario. I mean, there will be one or two of these on the test, but in general, when you get out there in the real world, if you're doing trig subs at every chance you get, you're probably not going to survive, right? It's a complicated process. It takes time out of your day. So if you don't have to do a trig sub, don't do a trig sub. Long story short. Okay, so what are trig subs? Trig subs are an attempt to eliminate radicals from your integrals. So if you see to the right, there's three kinds of radicals we can use this technique to kind of eliminate. And depending on which radical you see in your integral, that will tell you which trig sub you need to do. So an example of an integral where you'd want to do a trig sub would be something like this thing: 25x squared plus 4 all over x to the fourth dx. Okay, so you would be able to kind of do a trig sub, and it would eliminate this radical and turn it into just a trigonometric integral like in the previous section. Okay, so let's first introduce the appropriate subs. So if you see the form square root of a squared minus u squared, you're going to do an u equals a sine theta. Okay, so this will imply u equals a sine theta. If you see the form a squared plus u squared, that's going to tell you to do a u equals a tan theta. And then if you see the form u squared minus a squared, you're going to do the form u equals a secant theta. And there's a method to the madness, right? So note for like the second one, it'll align with the Pythagorean identities, so there's a nice cancellation. So for example, the second one, if you substitute in that u value that we're saying to use, you'd get a squared plus a squared tan squared theta. Then you could rewrite this as a square root of a squared times 1 plus tan squared theta. If you remember, what do we have? The sine squared plus cosine squared is 1, and then tan squared plus 1 is equal to secant squared. So we can replace this with a secant squared, and that will become the square root of a squared secant squared theta, and that will equal a secant theta, effectively eliminating the square root. Okay. There are some technical restrictions on these substitutions with regards to this angle theta. There will be inverse functions involved, so we always have these funny kind of restrictions that you'll see in the book over there on the right. So notice that cosine theta is greater than 0 because of this restricted range here. Generally, that restriction won't be too big of a deal for us. You can kind of ignore those little issues and just kind of fly by the seat of your pants. If they do become an issue, you're gonna, in my experience, you'll know. So you won't be able to do the problem at the end. You'll sort of walk into a brick wall. So you'll get an undefined expression. Okay. So anyways, they do show an example of that at the end of this section, and it has to do with the limits on the integral. Okay. So anyways, let's dive right in here and do some of these. So how to do this. So how to. Let's see if they have any examples for us, right? So in the book, what they do when they do these problems is generally they kind of do all the work outside of the integral, and then they stuff everything in the integral at the end. I like to kind of do everything inside the integral. Okay, so while I'm computing the integral, I'll do my substitutions. So it may look a little bit different. Like if you see down here where I just highlighted in blue, that's what I'm talking about. They kind of do all their work to the side and then do the substitutions. Okay, I'm just gonna, like I said again, my method is a little bit different, but I believe my method is probably superior. So that's my opinion. Okay. So anyways, it's 9 minus x squared, isn't it? We wouldn't be, yeah, okay. So first off, you want to identify the form. So the a is a constant. Above here on the left, the a is a constant, the u is a variable. So our u is x, okay? And then our a is going to be 3, right? So it's this thing that is dictating the u sub, all right? So I'm going to get my u sub. I'll say let x equal a sine theta, right? So 3 sine theta. Then what I like to do is kind of collect all the stuff I need. Like I said, they're going to figure out what is x squared to the side and then plug it all in. What I do is first get the differential, the dx. So that would be 3 cosine theta d theta. I like to draw a triangle, and they do right here. Okay. So to get the triangle, what I do is take this equation, this first equation, and solve it for theta. Okay, so I'll have sine of theta equals x over 3, and then theta equals sine inverse of x over 3. And believe it or not, that tells me how to build my triangle. So here's my triangle, there's my angle theta. Sine inverse, the input of sine inverse would be the output of sine, right? So sine as a ratio of sides of a right triangle is opposite over hypotenuse. So this input material here must be in the form opposite over hypotenuse. So that's what you put on your triangle on those sides. So the opposite side is x, hypotenuse side is 3. And then use Pythagorean identity to get the third side, right? So x squared plus the leg squared, whatever that is, b squared equals hypotenuse. So solve for b squared. And hopefully eventually you can just do that in your head. So b is 9 minus x squared. So right here, for the third side, you're putting 9 minus x squared. And that's really all the information you need to do this integral. Okay. And that's kind of what they're doing in the book, is collecting all this information. They do it in a real, in my opinion, haphazard way. But I like to keep everything clean and organized, because I've seen problems snowball and get carried away. And I just think this is the best approach. Okay. So I have all my information. Basically, to begin the problem, all you need are those first 2 items, and then the rest of this stuff, the triangle and stuff, that's for the end when you're doing back substitutions. Okay. All right. So first, I'm going to substitute in that material. I guess I shouldn't. I miscopied my integral. I put an extra dx in there for fun. I guess let's get rid of that. Okay. So in the numerator, I got 3 cosine theta d theta. In the denominator, I have x squared, so that's going to be 9 sine squared theta. And then I have the square root of 9 minus x squared again, so 9 sine squared theta. Okay. So in the book, I have an extra step in there, right? So in here, I have, in this first step where they say substitute, they've already kind of figured out what that square root thing is. Okay, they already simplified it. I just do it in-house, right? If you want to, you can kind of think it out right below. This is going to be the same as, 9 times 1 minus sine squared theta. That's going to be the same thing as 9 times cosine squared theta, using your trig identities, right? So remember, sine squared plus cosine squared is 1. So cosine squared is equal to 1 minus sine squared. Then you could take the square root of that, and you get 3 cosine theta. Okay, so I can replace that denominator now with so here we go. Integral 3 cosine theta d theta all over 9 sine squared theta times 3 cosine theta. And now I'm in line with the book, right? I just did an extra step. And okay. This cancels nicely. I can factor out any constants, 1/9. 1 over sine squared is the same as cosecant squared theta d theta, and I know that's just the antiderivative kind of cosecant, right? So I'm going to end up with 1/9 negative times cosecant, or rather it's cotan, right? So negative 1/9 cotan theta, cotan theta plus c. Okay, it kind of seems like you're done, but you're not. You began in x, so thou must end in x. So what you do now is use this triangle stuff, the second half of my box, to simplify it. So technically it's 1/9 cotan of sine inverse of x over 3. But this thing right here is just the theta in that right triangle. So you can use the right triangle in order to simplify this big, ugly, unwieldy expression here. We want to rewrite that as in terms of x in some sort of radical or rational or polynomial form. Okay, we want to get rid of the trig function. So we end up with -1/9, and then I use the triangle. I say the cotan of theta, so I go back to the triangle here. The cotan of this angle theta. What is the cotan as the ratio of sides of a right triangle? Well, it's 1/tan, so it must be adjacent over hypotenuse, right? So it's adjacent over hypotenuse. So you can literally replace this thing with that, adjacent over hypotenuse. Okay, so it would be times adjacent, which is square root of 9 minus x squared, all over hypotenuse, and then plus c. And you can see that's not what they have. What did I do wrong? No. 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 Oh my God. No. What is cotan? Oh, it's cotan is adjacent over opposite. Sometimes I swear. So it'll be, and then this is wrong, adjacent over opposite. It's been a while since I've taken trig. Okay, so adjacent over opposite. The opposite, instead of 3, you're putting x there. So you have an x, and then you're done. Okay, then you pretty much got it nailed. Okay. Okay. Let's move on to another example. This time a trig sub with tangent. So we're looking at example 2. Let's make this one the video quiz. This is the last video quiz and video quiz set number 4. So this is our 8.4 problem. It's example 2 from the book. So we have the integral of dx all over 4x squared plus 1 under the square root. Okay, so this time the form is a tangent form. You look back up here, the second form is tangent. Our u is going to be 2x, right? So we'll have u equals, so 2x equals, and then we want a tan theta. The a value this time is just 1, so 1, then tan theta, okay? Okay, I'm going to divide both sides so I can get my differential. So x is equal to tan theta over 2, and then dx will be equal to secant squared theta all over 2 d theta. Okay. All right, so that's what I need to begin. Then I'm going to take this guy as usual and solve for theta. So I'll have theta equals tan inverse of 2x. So as the ratio of sides of a right triangle, 2x, I can rewrite that as 2x over 1. And because we're dealing with tan, that must be opposite, I'll try not to screw that up again, over adjacent. Okay, okay, so on my triangle then, when I draw that out, here's my theta. Opposite must be 2x, and adjacent must be 1. And then the Pythagorean Theorem, so c squared equals 4x squared plus 1. So c must be the square root of 4x squared plus 1. So this side is square root of 4x squared plus 1. Okay, okay, so that's all I need for the integral. Now I like to just do it all inside the integral as opposed to the book where they kind of figure out the parts and then stuff it all in. Okay, okay, so dx in the numerator, I need to do a sub there. That will be secant squared theta all over 2 d theta. Downstairs, it will be square root of, so 4x squared now is tan squared theta plus 1. I can do some simplification on this. I have to remind myself of those identities, right? So sine squared plus cosine squared is 1, so therefore tan squared plus 1 is equal to secant squared. So I can replace all of that stuff with a big secant squared theta. So it would be square root of secant squared, and that will just equal secant theta. Okay, so let's rewrite it a little bit. I can factor out 1/2. I have the integral of secant squared theta all over secant theta, d theta. This is the easiest trigonometric sub-integral in the universe, apparently, secant theta d theta. And it tend to be much more involved in the homework. This will be 1/2. The integral of secant is going to be ln of the absolute value of secant theta plus tan theta, which is one of the ones you wouldn't necessarily have memorized. Okay, you would maybe have to look that up in a book. So it'd be 1/2 ln, and then I go back to the triangle to simplify this and this. Okay, so first doing secant. On the triangle, secant is what? It's 1 over cosine, so that's going to be hypotenuse over adjacent. So the hypotenuse is square root of 4x squared plus 1, all over the adjacent is 1, plus tan is going to be opposite over adjacent, so it'd just be 2x over 1, plus c, and then you could simplify it, 1/2 ln absolute value 4x squared plus 1 and the square root, and then plus 2x, and then plus c. Let's make sure that's what they got, yeah. Next, so weird rational powers. Don't be fooled. This is a trig sub problem. It doesn't look like one, but it is. So I have dx all over x squared plus 1 to the 3/2. So you know, how is this a trig sub? Where's the square root at, right? Well, you can rewrite this as x squared plus 1 to the 1/2, which is basically the square root, and then raised to the 3rd power. Okay, so it is technically a trig sub, although you can't see it. Right, so this form, again, is the tan form, and the u is just x. So we have x equals 1 tan theta. Dx is going to be secant squared theta d theta. And then for my triangle, theta is equal to tan inverse of x. And so here's my triangle. And of course, x in this case is going to be your opposite over adjacent. So the opposite will be x, and the adjacent will be 1. And then this third side from Pythagorean Theorem should just be x squared plus 1. Okie dokie. So I get the integral of dx is now secant squared theta d theta. Downstairs I have the square root of secant, whoops, x is tan. So tan squared theta plus 1. And then raised to the 3rd power. Let's do some simplifying here. So remember, tan squared plus 1 is just secant squared. And then the square root of secant squared will just be your secant theta. Okay, so I'll have the integral of secant squared theta d theta. It's the same answer, isn't it? Secant theta. And then that'll just be the integral of secant theta. And then that will be the ln of the absolute value of secant theta plus tan theta. And then that will just be the ln of the absolute value of square root of x squared plus 1 plus x. Let's see. Okay. Basically the same integral. Whoops. No, it's not. Not so fast, buddy. Oh, there's the cube there. I missed the cube. Oh, boy. I'm sorry. I'm sorry. It should be cubed. I was wondering. That was too good to be true. I was like, oh, this is awesome. No. Secant theta, d theta. The integral, 1 over secant. What is 1 over secant? That's just cosine. So this still isn't all that hard. So the integral of cosine is sine theta plus c, and then go back to your triangle. Sine is opposite over hypotenuse, so you get x all over the square root of x squared plus 1, and then plus your integration constant. Okay, great. So there's issues sometimes with converting the limits of integrals, and this is where you can run into problems with the trig sub itself. Okay, and they talk about that here in this remark under example 4. Example 4 works, right? You're going to be able to do that business as usual. Let's take a look at example 4. So we're actually evaluating from root 3 to 2, and we have x squared minus 3 all over x dx. Okay, so I'm going to get my material set up. So this is the secant version. So the u is just x, so I have x equals, and then a, because it's a 3, is just square root 3, so secant theta. And then dx will be square root 3 secant theta, tan theta, d theta. And then I solve this for theta, so I'll end up with secant theta equals x over root 3. And then taking secant inverse on both sides, I get secant, or theta equals secant inverse of x all over square root 3. And then do my triangle. So here's my theta. Secant is 1 over cosine, so it's going to be hypotenuse over opposite, or sorry, hypotenuse over adjacent. And then the third side from the Pythagorean Theorem, you get a squared plus, right, 3 squared is 3 equals x squared, so a squared equals x squared minus 3, so a equals square root x squared minus 3. So this side will be square root of x squared minus 3. Okay, so there's all my material. The book is going to convert the limits. What I'm going to do is leave the limits alone and then back substitute at the end to get everything back in terms of x, and then do my substitution. Okay, it's the same process. It's just their way was a little quicker. Okay, but anyways, here I go. I need a little more room. Okay, so the integral of the square root of square root 3 times secant theta squared, right? So that'll be 3 secant squared theta minus 3 all over x, which is root 3 secant theta, and then times dx, which is now root 3 secant theta tan theta d theta. Okay, so the root 3's will cancel. This thing up top, let's figure out what that's going to be, right? So I can factor out the 3. I get secant squared theta minus 1. Remember your identities. So sine squared plus cosine squared is 1. Tan squared plus 1 is secant squared. So therefore, tan squared is equal to secant squared minus 1. Right? So this will be root 3 tan squared theta, and that will be root 3 tan theta. Okay, so I'm going to end up with the integral of root 3 tan theta all over secant theta times secant theta tan theta d theta. Secants cancel, factor out the root 3, so you get root 3 integral of tan squared theta d theta. Then you need the Pythagorean identity again, so tan squared is secant squared minus 1, squared theta minus 1 d theta, and then we can integrate that pretty easily. So root 3 times tan theta minus theta. We have to evaluate it. I'm going to back sub, okay, unlike the book. Okay, let's do it like the book does it. I'm not going to be a rebel anymore. So what were the original limits? So root 3 and 2. Okay, so root 3 and so x is root 3, and then we want x is equal to 2. So you can plug it into this guy right here. So you'll have theta equals secant inverse of root 3 over root 3, which is 1. Secant inverse is just like cosine, right? So it's really 1 all over cosine inverse of 1. Cosine inverse of 1, and you have to think about the range of cosine inverse. So the range of cosine inverse is from 0 to pi. So cosine inverse of 1 yeah, so no, this is not true. That presumption, you cannot make that. Let's think about what cosine is and what secant is and what inverse secant is. So cosine function, no, we're right here. And then the secant function is going to live off of cosine like this. So it does have asymptotes, so you have to watch out for that. But, you know, secant inverse is asking what? Well, it's asking the secant of what angle is equal to 1. And clearly, the secant of 0 is equal to 1. So the secant inverse of 1 is just going to be equal to 0. And then, oh my God, for the other one, we have theta equals secant inverse of 2 all over root 3. So this one I kind of think in terms of cosine inverse, but kind of, right? So I could see that root 3 over 2, the cosine of what angle equals root 3 over 2, and then kind of play that game. The problem with secant inverse is if you play that game, you're saying the cosine of, you know, the cosine of what angle equals 1, well, it's 0, but then 1 over secant of 1 over secant of 0 is undefined. So you see what I'm getting at there. Anyways, so for this problem, the way I kind of think of it is the cosine of what angle is root 3 over 2. So I take the reciprocal of that thing, and well, I guess I could have done the same thing up here then, right? So that would have worked. I don't know why my brain is just not, I don't deal with secants very often, I guess. So here I'm asking myself the cosine of what angle is 1, right? And that would just be 0. I'm sorry. If I could, I would go back and remake an entire new video, but no. Okay, so anyways, the cosine of what angle is root 3 over 2, and we want it to be in this interval from 0 to pi. So in that case, it's going to be 1/2. Okay, is that true? 1/2. Oh, sorry, it's a pi over 6. Jeez. There we go. All right, so on my limits then, I'm replacing 2 over root. I'm replacing root 3 with 0. That's painful. That's why I wanted to switch back in the terms of x. And then I'm replacing 2, the upper limit, with pi over 6. Oh my God, I'm so sorry. All right, so here we go. Let's evaluate that. It'd be root 3 times tan of pi over 6. Oh my gosh, that's sine over cosine. Sine of pi over 6 is 1/2 all over root 3 over 2. So that's going to be 1 over root 3 minus pi over 6 And then, of course, tan of 0 is 0, plugging in 0 for theta is 0. So we end up with that object as our answer. Let's just make sure that's true and jives with what the book has. Of course, they wrote it in a different form, so let's see if I can get it into their form. So this will be 1 minus pi root 3 all over 6. Yeah, it's the same thing. Okay, the issue becomes when you try to pick these other limits, and you'll have trouble when you're doing that conversion process like I just did. Okay, so if you pick on the right there x to be negative root 3, and then x to be for the lower limit negative 2. You just need to be careful with this conversion, right? So again, I'm thinking, let me try to redeem myself. Given that theta equals x over root 3, secant of theta equals x over root 3. So theta equals secant inverse of x over root 3. So in this particular case, theta will equal secant inverse of negative 1. Okay. The other guy, theta will equal secant inverse of negative 2 all over root 3. And you need to make sure that your angles that you're getting your hands on are in this range, okay, from 0 to pi. In particular, we're going to have to choose, so these are negative. So for the first one, I'm asking myself the cosine of what angle is negative 1. And of course, that will be just pi. That's this point over here. And then for the second angle, I'm asking myself the cosine of what angle is negative 2 over negative root 3 over 2, right? So you just take the reciprocal, negative root 3 all over 2. And you don't want to pick like the one in the fourth quadrant. You want the one that's in the second quadrant. So the reference angle for root 3 over 2 is pi over 6, but we want this one in the second quadrant. So it's 1, 2, 1 pi over 6, 2 pi over 6, 3 pi over 6, 1 pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2, 4 pi over 6, 5 pi over 6. So here theta would be 5 pi over 6. Okay. So, and that's, you can see that's what they used as their bounds. So you have to be aware of the kind of restrictions that you're dealing with whenever you have an issue like that. If you just kind of did it without thinking too much, you would end up with like an undefined issue popping out at the end of the day. So I don't know. If it, it's an issue, but it really won't come up all that very much. So you need not kill yourself about it. Okay. So anyways, applications, we could use this to find arc length, fluid forces. Let's see what else they have. These are just a bunch of applications. Okay, let me probably look at one that's a little more complicated, right? These all seem, the examples in the book all seem kind of easy, but let's try number 7. Let's see how that goes. Let me move my board over a little bit. Okay, so number 7, we have 1 all over x times the square root of 9x squared plus 64 dx. Right. So in this case, the u is going to be from here. So we're going to let u be our 3x. And the form tells us a tan. And the a value is from here. It's 8. So 8 tan theta. I'm going to solve for x so I can get my dx. So I'll have 8 tan theta all over 3. So dx will be 8/3 secant squared theta d theta. I'm going to go after my triangle material. So solving this equation, I guess, or even this equation, you're going to get tan theta equals 3x over 8, and then theta will be tan inverse of 3x all over 8, and then you can do your triangle. So opposite over adjacent, and then Pythagorean theorem give you the other side. So this will just be 9x squared plus 64. Okay, then I'm going to start doing my substitutions. So you really only need this first part in, just pull this first part off. So the integral of 1 all over x, x is 8/3 tan theta, and then this junk, okay, the square root of, it'll be 64 tan squared theta plus 64, and then dx, which is 8/3 secant squared theta d theta. Okay. I can see a nice cancellation here between the 8/3. This thing then is the square root of 64 times tan squared theta plus 1. And then, of course, that's equal to the square root of 64 times secant squared theta. And then, of course, that's 8 secant theta. So I'm getting the integral of, let's move the secant squared into the numerator, secant squared d theta, all over tan theta times 8 secant theta. And then we can factor out the 8, get rid of one factor of secant. So we have 1/8 secant theta d theta all over tan theta. So what it always ends up as is a trigonometric integral from the previous section. Okay, you just have to figure out a clever way to dispense with this integral. I'm not exactly sure, so what I like to do is, if I'm not sure, just convert everything into cosines and sines and then simplify. So secant is just 1 over cosine of theta. Tan is sine theta over cosine theta, d theta. And then I'm going to do a reciprocal, so I have 1 over cosine theta times cosine theta over sine theta, d theta. Those will cancel out. I get 1 over sine theta, so I got 1/8 integral. 1 over sine theta is what? Let's say cosecant theta, right? D theta. And then you may need your tables to get that integral, but it's negative ln absolute value of cosecant theta plus cotan theta. This is an indefinite integral, so we go plus c. Then I need my triangle again. So if you don't mind, I'm going to just copy this triangle and bring it down a little bit. Move down. Oh, you. Of course. Thank you so much. And it's going to do it again. Okay, so anyways, I apologize. I need my anger management classes. Negative 1/8 ln absolute value cosecant is the same as 1 over sine. So it's going to be hypotenuse over opposite. So square root of 9x squared plus 64 all over 3x. Plus cotan is going to be adjacent over opposite, so 8 all over 3x plus c. You can literally leave it like that, just plop it into the machine. Let the machine do the work, I guess. Where are you? What was that? Is it this one? Negative 1 over 8 ln, I need absolute values, ln of the square root of 9x squared, this 6x, and then all over 3x, and then plus 8 all over 3x, and then plus c, and then drum roll. Oh my god, no. It's 9x squared plus, how about 6? 64. Oh my gosh. For some reason I miscopied that as a 6x. And I can't find a stupid triangle anymore. It's supposed to be 64, not 6x, buddy. That better be it. Or I'm going to flip out. I'm just going to lose it. Yay! Let's do one of these ones that maybe are more annoying. Then I'll call it quits. Number 12 and 13, A and B are going to be the same answer. Yeah. I don't think there's any issues with the domain and stuff on those. I don't think any of them have those issues like I was going over with the you know. Let's try, I don't know. Which one? Let's try number 10, I guess. No, let's try number 11, because that looks funny. Okay, and then I'll call it quits. Number 11, the integral of x all over the square root of x squared minus 16x plus 39 dx. Okay, I'm going to have to complete the square for this thing to even see kind of under the hood what I'm dealing with. So the square root of x squared minus 16x plus negative 16 over 2 squared. So negative 16 over 2 is negative 8. Negative 8 squared is 64. I have to immediately subtract 64. Okay. That will be the integral of the square root of x minus 8 squared minus well, that's nice of them, 25. Then my u this time is the x minus 8 stuff, and the a is 5. It's a secant version. So we have x minus 8 equals 5 secant theta. I'm going to solve for x to get my differential. So 5 secant theta plus 8. So dx looks like it's going to be 5 secant theta tan theta. Then I'm going to get my triangle material, solving this thing for theta. Theta will equal secant inverse of x minus 8 over 5, when all is said and done. Then I need my triangle. Theta here. Secant is 1 over cosine. Cosine is adjacent over hypotenuse, so this will be hypotenuse over adjacent. And then solving with the Pythagorean Theorem, the third side, I'll have x minus 8 squared minus 5 square root of, or 25 rather. Sorry for doing it in my head, I get it wrong. And then we should be able to rock and roll. So I have the integral of 5 secant theta plus 8 all over the square root of so it's going to be 25 secant squared theta minus 25 times dx, which is 5 secant theta tan theta, d theta. Lost my d theta in there. And then we can kind of simplify this, right? So that's just be 25 square root of 25 times secant squared theta minus 1. That'll be the square root of 25 tan squared theta. And of course, that will be 5 secant theta, or 5 tan theta, sorry. Square root of tan squared is tan. All right, so rewriting my integral a bit. There's going to be, let's see. So I got 5 secant theta plus 8 all over 5 tan theta times 5 secant theta, tan theta, d theta. I can get rid of the 5 and the tan theta like that. I'll end up with the integral of 5 secant theta plus 8 times secant theta d theta. So that's going to be the integral of 5 secant squared theta plus 8 secant theta d theta. That first integral you should know is just 5 tan theta. The second integral, maybe have to look up, 8 ln absolute value of secant theta plus tan theta. The way it's coming up in the homework, maybe you should have it memorized, but I don't, just because it comes up so much. But I wouldn't do that on a test. Anyways, let's convert back now. So 5 tan, using the triangle, tan is opposite over adjacent, so it's going to be times the square root of x minus 8 squared minus 25 all over adjacent, which is 5, plus 8 times the ln, or the absolute value secant, is basically 1 over cosine, so 1 over cosine. So that would be hypotenuse over adjacent, so x minus 8 all over 5, and then plus that thing we just had, x minus 8 squared minus 25 all over 5 plus integration constant. And I'll simplify it a little bit as I put it into the machine. The 5s would cancel on the first part. I don't know which one I'm even doing, number 11. 5s cancel in the first part, so you get square root of x minus 8 squared, whoops, that's going to kind of force me to get rid of that, squared minus 25, and then plus 8 ln, be the absolute value. First is x minus 8 all over 5. So the fraction first, x minus 8 all over 5, and then plus fraction, the numerator, square root of x minus 8 to the second power minus 25 all over 5, and then plus c, and then you do a drum roll. Oh my god, I finally got one. All right, so anyways, yeah, these problems are definitely longer than the typical ones you're used to, so just hang in there. It'll really put some mathematical hair on your chest, so to speak. And as usual, thank you for watching, and sorry about all the mistakes in this video. I made a lot of mistakes, but hopefully it wasn't too confusing. Anyways, as usual, thank you for watching, and the video quiz was example 2, and I will see you next time.